We are starting chapter 5, and the next topic that we will talk about is hypothesis tests and confidence intervals. So we have population model, which is unknown for us, and we have our sample model or estimate. When we calculate the values of our coefficients in a sample, we want to test whether these coefficients are statistically significant in the population. Do we really have a significant relationship between our independent variable and our dependent variable? So, in the class size example, the question will be, is the slope statistically significant, meaning beta 1 hat. So, we will make two-sided tests for beta 1 hat. And it goes like this. So null hypothesis will be that beta 1 is not statistically significant, or in other words, that beta 1 in the population is equal to hypothetical value, which is equal to 0. Alternative hypothesis is saying that beta 1 is statistically different from 0 in population, and it is statistically significant, so that class size really statistically significantly influencing test scores. So what are the steps of testing hypothesis? First step is to calculate the standard error of beta 1 hat. This is formula, but anyway, we will get the value of beta 1 hat from the Gretel. Second step is to find t statistics. So we will conduct t-test, so-called t-test. So as you can see, we need beta 1 hat. We will have that from our model. We need to have hypothetical value of beta in population, which is 0, and we will have our standard error. Next step can be to find p-values. This is another way of testing hypothesis. P-value is minimum probability under which null hypothesis can be accepted. A p-value of less than 5% provides evidence against null hypothesis. So if it is very small, then null hypothesis will be rejected, and we can conclude that beta 1 is different from 0 in population. The probability of obtaining a value of beta 1 hat at least as far from the null as that actually observed is less than 5%. When we are calculating p-value, we are usually comparing it with a level of significance of 1%, 0.01, or with the probability of 95%, which means the significance level is 0.05. So let's go back to t-test. So if we do everything with a probability of 95%, these are the limits, and this is the area of accepting the null hypothesis. This is two-sided t-test. These are actually critical values from statistical table of normal distribution, but a very similar value is for t distribution also, minus and plus 1.96. So if t is in absolute value less than 1.96, we will fail to reject the null. We will actually accept the null hypothesis, saying that beta 1 in population is really equal to 0, which means, in other way, that our t statistics is somewhere here in this area of accepting the null hypothesis. If t is larger from 1.96, which means actually that it is here somewhere, or here, then we will reject the null, saying that beta 1 is statistically significant, and that independent variable x is influencing statistically significantly our dependent variable y. So let's go to our example. This is the equation that you already seen, that we have calculated. So this is beta 0, this is beta 1, and these are the standard errors of these two coefficients. So we need this in order to test if slope is statistically significant. Usually we are testing the slope, but you will see that we will test also the beta 0. So we know also that R squared is 0.51, standard error of regression. And now we wish to test the following. We wish to test if our beta 1 in population is equal to 0. Alternative hypothesis x1 is claiming the opposite. So again, we will calculate the t-statistics. We already know these three values. So beta 1 hat is 2.28, beta 1 0 is 0, and standard error is 0.52. Here it goes. So t-statistic is minus 4.38. On the graph, we see the t-statistics is far in the area of rejecting the null hypothesis. So we will accept the alternative hypothesis. And p-value, you will see it as an output of the software that this is less than 0.05 because probability is 95%, which means that the level of significance is 5%. So this is another proof that we are rejecting the null hypothesis. Okay, let's go to our Gretel example to see how it works in Gretel. So we will make a model, ordinary least squares. Test scores are here, dependent variable, independent student-teacher ratio. Please mark this option here, robust standard errors. Later on we will explain what this means. Okay, so we have the results. And here you have t-statistics, minus 4.389, as we got it here. Also, we have p-value, so it is 1.45 on the power of e minus 0.5. So it means that you need to add 5 zeros before this first number. So it is 0.0000145. So because it is less than 1%, 0.01, this is why we have 3 stars. If it is between 0.01 or 0.05 and 0.05, then you will get 2 stars. If it is between 0.05 and 0.1, there will be only 1 star. So we have already tested the beta coefficient. Beta 0 is also statistically significant, as you can see. So you will get this output automatically in Gretel. Okay, let's go back to our presentation. We can also conduct the one-sided t-test, but we cannot use the software here. We need to do it by ourselves, but it is actually really straightforward and very easy to do it. For example, is beta 1 always negative? So the null hypothesis will still be the same, and the null hypothesis will be that beta 1 is less than hypothetical value, which is 0. So we have the upper limit, we have the maximum. If we are interested, we can put something other here, something else here, maybe number 2 or number 5. It depends on the practical problem what we want to test. Maybe we are interested to check if beta 1 is in population less than 10. But this time we are just checking if beta 1 is always negative. So again, we will calculate the t-test, the t-statistics. It will be again the same value, minus 4.38. What is changing is we are changing the limits. So if we have in the hypothesis upper limit, it means that our limit here is, from a statistical table will be critical value will be only negative, and for 95% it is minus 1.46. And again, our t statistics is less than this limit. This is the area of rejecting the null hypothesis, which means that we will reject it and saying that beta 1 in the population is always negative. Also, p-value will be less than 0.05. The other variation is that if we have a lower limit, for example, if beta 1 is always positive, which means in our example that beta 1 is larger than hypothetical value, which is 0. Again, since we have the lower limit, now it is larger than larger than 0, our critical value will be always positive. All level of significance is on the right hand side, and this is the area of rejecting the null hypothesis. But our t statistics is here in the area of accepting the null hypothesis. So it means that we will accept the null and saying that we cannot accept the null that t statistics that beta 1 in population is always positive. Also, p is larger than 5%. When we are testing beta 0, it is practically the same. Usually we are testing if it's equal to 0 or not. And now we go to the next title, which is confidence intervals for regression coefficients. We are actually want to answer this question. What are the reasonable ranges that one of the coefficients can take in the population? Because we got our coefficient in the sample, and we know that we are a little bit on the left or on the right from the true value of beta 1 or beta 0 in population, and we want to calculate the interval for that. There are two equivalent definitions. One is confidence interval is a set of values that cannot be rejected. So to tell the intervals, we will have lower limit and upper limit, usually with 5% significance. Second, it is interval that has a 95% probability of containing true value of coefficient. So 95% confidence interval for beta 1 is this. So this is lower limit, this is minimum, this is upper limit or maximum. So again, what we need here is our value of beta 1 hat in our model, critical value from statistical table. For 95% it is 1.96. On the left side it is negative, on the right hand side it is positive. And also we need standard error that we already have. So if when we calculate this, we can say that we can expect with the 95% of probability that value of beta 1 in the population is inside these two limits. So when it comes to test score example, we know these values. Beta 1 hat is minus 2.28, standard error 0.55. So we enter everything in the equation, and these are the limits. So you can also notice that beta 1 is always negative, which is in line with these two hypotheses that we rejected before, that it doesn't contain 0 in it. How we comment on this? With 95 probability, we can expect the true value of beta 1 in the population will be between minus 3.3 and minus 1.26. Let's go to the example first. So we are starting our model. So I'm not using the menu, the general menu in Gretel. I'm using the menu that is related to my model that I already have. I'm going to Analysis, Confidence Intervals for Coefficients, Enter, and here it is. So we have calculated the interval for beta 1 for student-teacher ratio, and here it is. So it is always calculated 95% of confidence, and lower limit is minus 3.3, upper limit minus 1.25. Also, we have the intervals for our constant, for our intercept or beta 0 hat, beta 0 actually in population, and it goes from 678 to 719. Exactly what we got here. Okay, last topic is confidence interval of predicted effect of changing x. So what will be the value of our dependent variable y for certain value of x? But instead of saying that one value on the basis of our equation, we will calculate the confidence intervals, because we know that there is some variations in the data in population, and we cannot predict for sure that it will be one number. We will say that we can expect that value of y in population will be between two limits. So we have our equation. We will put x in the equation and calculate the y. Also, we can calculate the change of y due to change of x. For example, if student-teacher ratio goes up by 2, what will be the test score? So it is minus 4.28. So we have delta x, it is 2, because we are changing student-teacher ratio by 2, delta x is 2. And you see that already here in interval we have the same values for confidence interval for beta coefficient that we already done before. So beta 1 hat is minus 2.28, standard error is 0.55, statistical critical value minus 1 or plus 1.96, and change in x is minus 2. When you put everything in the equation, this is lower limit, this is it, here, and this is upper limit, here, this part. And the result is 6.6, 2.50 time. So 90% of time we can expect, if we increase student-teacher ratio, if we reduce student-teacher ratio by 2, that changes in test scores will be inside the interval of 6.6 to 2.52 test points. So if student-teacher ratio goes down by 2, with 95% probability, we can expect the test score will be between 2.55 and 6.6. Will be increased by 2.55 and 6.6 test points. This is the end of presentation.